Unit Operation Classroom, an initiative of unitoperation.com. We are discussing now here GATE 2024, question 64. A PD controller, professional derivative controller with transfer function GC, so this is the controller transfer function which is already given, is used to stabilize an open loop unstable process. We'll see what kind of an open loop unstable process it may be with a practical example with transfer function GP. So this is the process transfer function, and the times in minutes. Okay, from the necessary condition for closed loop stability, the maximum feasible value of tau t we have to find out. Okay, so this is a closed loop transfer function which is very easy, and the characteristic equation which is DC. That is GOL, and from there we get once we substitute these here, we get this equation here, and the details. This is a little bit of involved process, but the details are shown here. Okay, and once you do that, then you arrange these terms in the route array. From there, you get this things, because all of them, the first column have to be positive. We know we get the tau t maximum is 22.2 minutes. That's the answer. So this is my answer. Okay. Now, we just want to give you a practical example of this one. Typically, let's say in an industry, so this is, let's say, CSTR here with a cooling jacket, and there's a coolant flow. There's a coolant flow here. For a typical single input and single output CSTR, this might be a transfer function. This might be the transfer function which you have seen here. This could be a typical transfer function of the process. Okay, for a CSTR with a cooling jacket. As you can see in the for this one, contributes to right half plane pole at +1. So that of course leads to instability. It's about 1 minute. And this one, of course, is the first order, contributes to the first order process. And this really comes from the heat capacity of the reactor, or the coolant flow dynamics, or the sensor delay, etc. Let's quickly discuss, why there is a problem. Let's look at the Van Heerden diagram, which is a very standard exothermic reaction in a CSTR diagram here. So this, I'm not going to the detailed discussion in the Van Heerden diagram. This, of course, is the rate of heat generation inside the reactor. And of course, you can see there's an exponential rise. That's because we have the Arrhenius factor. There is an exponential term there, and this is where actually the reactant just levels out. That's why it just levels out here. And this, of course, is the coolant flow, the heat removed by the coolant, and this we know heat removal by coolant is a linear dynamics. So that's what we get here. So this is the heat generation inside the reactor, and this is the heat removal inside by the cooling jacket. And wherever they intersect, these are called steady states, and we know this is these two are stable steady state, and this is an unstable steady state. And of course, the derivative action becomes important as long as this is the rate of temperature rise temperature rise due to heat generation becomes much higher than the rate of cooling. That's where you really cannot stop the reactor. It just goes on, and this is called the reaction runway. Means it ultimately leads to an explosion or total destruction of the batch. So this is a highly undesirable. A lot of times depends upon the actual value. So, so as I say, this could be a typical this for this process GPS. This could be a typical example. Might be this one. Okay. So how do you control this one? So this is my PD controller. For the controller, of course, a manipulated variable would be coolant flow, and the controlled variable, of course, is going to be the reactant temperature inside here, and controller controller, of course, we are using PD controller. Okay. What are these terms? What do these terms do? This term here, of course, as you can see, there is, of course, reacts to the temperature. That's just T set minus T measure at all times. It just measures linearly what's the difference between the two. And according to the value of this proportional term, it just reacts and opens the control valve. This is important because this reacts to the rate of change of temperature. So, which is very important in terms of the Van Heerden diagram here. Uh, if this rate becomes the rate of generation that becomes too high, then of course it leads directly to the reactor instability and reaction runaway. If the T reactor rising too fast suddenly, let's say for some reason, the derivative, and what happens because this is unstable, slightest change in the parameters might lead to the reaction runaway. So it's very important to have a good control. And so, if the temperature rising too fast, reaction runway, the derivative term kicks in and it opens the coolant valve rapidly to stabilize the reactor temperature. Okay. We have seen this is the maximum value of tau d we can put in. If we put too high value, then the system overreacts and the system becomes very oscillatory, the response, and that is difficult and must be avoided. So for all practical reasons, might be we will choose somewhere between 5 to 10 minutes. The exact value will depend upon a proper simulation of the system. So the proper simulation of the system. So this is the value of so this is my answer.